Welcome, everyone. My name is Ali. I am very excited to be here and to present our work. Today, I will talk about our paper, Domain Adaptation for Structure Health Monitoring. This is going to be the layout for the presentation. United States has one of the most sophisticated infrastructures in the world. However, a recent study conducted by the American Society of Civil Engineers found out that United States infrastructure is aging. ASCE graded the infrastructure as a D+, which is something you don't want to show to your parents at home. The cost to rehabilitate this infrastructure is a whopping $4.6 trillion, and failure to act may cost an economical loss in GDP as big as $3.9 trillion by 2025, and more later. Overall, it is economically not viable to replace all deteriorating infrastructure due to the limited amount of resources. The operations of maintenance, repair, and replacement should be prioritized accordingly. Structure health monitoring is particularly useful if you want to tackle the infrastructure problem by prioritizing the MRR, because we want to extend the structural life cycle as efficiently as possible. SHM is essentially the process for characterizing the integrity of structures and detecting the damage if there is any. In the last few decades, SHM gained a lot of momentum, especially the introduction of machine learning enabled further refinement in recognizing the structural damages compared to traditional SHM methods. Among many applications of machine learning, supervised methods are particularly useful since they offer better results for damage detection and localization. However, there are some inherent issues with supervised ML-driven SHM. Experimental data is not always available. Furthermore, it is an unrealistic expectation that we can obtain this data without harming the integrity of the structure before its actual deployment. We could generate labeled data set for training using a representative finite ML model, where introducing damages is a more cost-effective approach. A majority of machine learning applications assume that the training and testing data has similar distributions. However, it can be often a challenging task to produce a high-fidelity FEM that represents the actual structure. So, divergence between the training and testing data is unavoidable. This is also known as domain shift. Our hypothesis is that there exists some unobservable map of invariant features that can generalize over source and target domains well, even in the case of domain shift. Following that, our objective is designing a machine learning-based architecture that can predict correct classes across both domains in the presence of domain shift. A minimum soft requirement for domain shift is that the conditional distributions remain same for training and testing, but input distributions are changing. However, for more general cases of domain shift, the conditional distributions does not need to remain same either. For a general case of domain shift, we have the source domain, DS, which contains the labeled source samples, and the target domain, DT, which consists of unlabeled target samples. We assume that the distribution, specifically the probabilistic distribution, for both domains are different, which implies that neither the conditional distributions nor the input distributions match for testing or training. In this case, we mean source and target domain data. One last observation regarding the domain shift is that we have an unobservable latent space X0. The label Y for a given input is dependent on this latent X0, whether the data is coming from source or the target domain. However, we may have some map into the observable space. In this case, the training and the testing data is a projection of X0, through a function called f, which is basically the mapping itself. All right, let's summarize what we have so far. We have here source and target domains, and there is a domain shift between them. They don't have the same distributions. Under domain shift, a classifier trained with source data will mispredict the label for the target data. The purpose of domain adaptation is finding a mapping function that can minimize a probabilistic discrepancy metric between those two domains. Ben David et al. Stated that a classifier-induced divergence criteria, namely edge divergence, is sufficient for domain adaptation. Edge divergence relies on distinguishing the examples of DS and DT. Furthermore, edge divergence states that for proper domain adaptation, we need to train a classifier GX that can label the data from DS and DT accordingly. In this case, 0 if it is coming from the source domain, 1 if it is coming from the target domain. Then the objective is maximizing the error between the learned model, GX, and the true model, HX. In other words, we want the classifier not to be able to distinguish between the two domains. With the maximum domain confusion, the classifier will think every example is coming from source domain. This is a nice way to minimize the probabilistic discrepancy between the two domains. There are inherently two tests for implementing domain adaptation using edge divergence. To achieve these tasks, we use domain adversarial neural network approach proposed by Gannon et al. First, we want to design a label predictor to correctly predict the class for the source domain data. This is the part where the network decides on whether a structure is damaged or not based on the features that we extract from the input. Please note that the label predictor cannot be trained on target domain data as the target examples are not labeled. In the second step, we want to train a domain classifier that can discriminate between source and the target domain. This task utilizes both domain data. During the training of the neural network, both components act like feed-forward neural network. Again, remember our aim. It is maximizing the domain confusion. Now, in order to achieve a domain adaptation, we need to cheat the domain classifier such that it will not be able to discriminate between source and target. To do that, during the backpropagation phase of the training, a gradient reversal layer, denoted as GR in the figure, is added to the architecture to learn the latent features of both domains. In this case, it's going to be X0. This layer is essentially reversing the gradient learned from the domain classifier by multiplying it with a small negative number. In other words, we force the network to unlearn the domain classification such that the distribution of latent features extracted from both source and target domain will be indistinguishable. That means the feature extractor is expected to learn domain invariant features. Now we discuss our approach. We want to evaluate it for SHM applications. We relied on two different data sets. One of them is Gearbox fault detection dataset introduced by PHM Data Challenge at 2009. For this Gearbox, acceleration data were collected at the input and output shaft of the gearbox at different speeds under two different loading conditions. For each shaft speed and loading conditions, 6 fault types are simulated. Here are some of the faults at the gears. For each case, about 4 seconds of vibration data is collected at a very high sampling rate, twice. The frequency domain provides a rich feature set for fault detection using vibration data. Thus, before training, all the raw data is converted to the frequency domain using sliding window fast Fourier transformation, also known as the short time Fourier transform. After pre-processing, each damage condition case has about 2,700 data points with 601 features per condition. The dataset is divided into source and target domains according to the loading conditions. The source domain corresponds to the low load condition, whereas the target domain is composed of high load operation. Both domain data is split into training and testing data using 4:1 ratio. And our task is detecting the type of the fault correctly, regardless of the shaft speed or loading condition. So we developed 2 models to evaluate the domain adaptation approach. The model 1 is source-only model, which is trained only with the source domain data. Model 2 is the domain adaptation model, which is a domain adversarial neural network in this case. It uses both source and target domain data to discriminate the domain and also to predict the correct label for the damages. During testing, however, we still use the upper part to predict the damage. The architectures and numbers of neurons are shown in this figure. The feature extraction layer is colored in green. Label prediction layers are blue. Domain classifier is orange. The network is a combination of densely connected neurons with some dropout. This table shows the accuracy for source and target domain test data on the source-only model and the DNN model. We also provided transfer component analysis, TCA method, as a reference. That is a traditional domain adaptation method. The accuracy for predicting the source data is about 97% for both models. Without domain adaptation, the accuracy of the target data for the source-only model is 64%. The DANN improves the prediction on the target data and increases the accuracy to 71%. And among all of them, TSA produces the lowest accuracy for both source and target domain data. By looking at the results, we can say that DANN outperforms source-only model and the TSA, and the improvement for the DANN over the source model is about 10%. Our second evaluation case focuses on the Los Alamos 3-story structure. The structure is excited with an electromagnetic shaker attached to its base. The acceleration at each floor, including the base, is recorded. We considered 7 damage conditions where the stiffness of various columns are reduced. Again, we applied the SDFD analysis to get the frequency domain data for pre-processing purposes. Also, for this case, we assumed we don't have access to labeled experimental data. Thus, we wanted to train the network using only finite MM model data and test it on the experimental data. Then in this case, the source domain data is going to be the FEM data, and the target domain data will be the experimental data. We followed a model architecture similar to PHM data for this case. During the source domain data generation, we deliberately mismodeled the finite ML model by about 10%. Our preliminary results show that the accuracy for predicting the source data is almost 100% for both models. Without the domain adaptation, the accuracy of the target data is 36%. And the DANN increases the accuracy for target data to 63%. Our preliminary results imply that when there is some divergence between source and target domain, we can get almost 100% of improvement. Now, to summarize our paper, for many machine learning-based SHM applications, the experimental data is often limited. So we need to train a model with what we have and what we can generate using an FEM model. However, we should expect that there will be a domain shift between source and target domains since the data distributions are not same. Without addressing the shift between the domains, it is challenging to train a machine learning model that can work well for SHM applications. Under divergence, we showed that the machine learning models may predict the labels incorrectly. Our study shows that domain adaptation is a viable approach to damage classification problems under domain shifts, and we have demonstrated that the DANN increases the classification performance compared to a no adaptation approach. Here are some possible future directions. Target domain data labeled as normal or undamaged is accessible for training to some extent. We could argue that it can be used to improve the domain classifier and probably the label prediction as well. For this study, we use shallow densely connected networks. There may exist a better representation mapping by utilizing convolutional networks. This is another way to improve the prediction performance. Other domain adaptation strategies should be also explored. We only looked at TCA in this study. There are GAN-based discriminative approaches, which is very similar to DNN at some extent. Those approaches are very promising. And it seems to be those approaches are the right step for machine learning-driven SHM applications. This is the end of my presentation. I want to acknowledge DARPA for supporting this research. I also want to appreciate IBM for its support. Thanks for your time and interest. I will be happy to receive your questions now.